All right. Good morning, everybody, and welcome back to the CIB Presidential Seminar Series that we broadcast from Purdue University. As you all know by now, that the theme of our seminars this semester and last semester are distinguished women researchers in the built environment. And today, indeed, we have a very distinguished colleague, Dr. Iris Tommelein. And let me give a brief introduction of her achievements. It's not complete, but just a brief introduction. So Dr. Tommelein has a 5-year degree in civil engineering and architecture from the Free University of Brussels in Belgium. Then as a graduate student at Stanford University, she earned an MS in civil engineering, construction engineering and management, and as well as a MS in computer science in artificial intelligence. After that, she finished a PhD in civil engineering, also with a concentration in construction engineering and management. And now she is a distinguished professor, as I mentioned, at the University of California, Berkeley. Iris and colleagues found the Lean Construction Institute in 1997. Many of you, I'm sure, have heard of that and participated in it. And the UC Berkeley's Project Production Systems Laboratory, P2SL, in 2005. Iris is a leading member of the International Group for Lean Construction, IGLC, and a member of the National Academy of Construction. She received LCI's Lean Pioneer Award in 2015, the Project Production Institute Technical Achievement Award 2022, and this year became the first woman to receive the ASCE Construction Management Award. So with that said, please welcome Professor Iris Tommelein.
Thank you very much, Professor Hastak, for inviting me to give this presidential lecture and also to give me the opportunity to do it in person. I very much prefer actually seeing people and interacting with them than being totally on Zoom. So it's an honor and a pleasure to be here. I thought I should give maybe a little bit more background. Let me figure out all the controls here. On who I am. So I actually joined the International Group for Lean Construction that was founded in 1993. I joined the group in 1996 after I spent a year working on a large oil refinery project and studied materials management and supply chain management. As Professor Hastak already mentioned, at the time we understood that certain things in our industry were broken. So my background was in my PhD dissertation was in site layout and materials management. And at the time, I was reading all the books I could possibly read about the topic, which was not too hard to do because there were not many books on the topic. And many project management books, and still today, talk about managing resources. And what are the resources? Time and money, of course, manpower, materials, and machines. That makes 5. And there's one more resource that I was particularly interested in and that typically gets overlooked even though it is omnipresent, and that's the resource space. And so you will appreciate that if the word isn't even mentioned in project management textbooks, that there may be a problem in how we understand project management and what needs to be managed. So that was my first sort of, what's wrong here in this picture? So I spent a year on this large oil refinery, and then I met some colleagues once I joined the faculty at the University of California, Berkeley, who had also had similar moments about what's wrong with our industry. And we had some ideas as to how we could begin to fix our industry and improve it, and that's why we started the Lean Construction Institute, implementing new planning systems and talking about reliability and performance and the likes. With that in mind, though, after several years of implementation and working with industry, we realized that we had more questions than ever about how to improve performance in our industry. And so my colleague Glenn Ballard and I started what is called the Project Production Systems Laboratory at UC Berkeley, and we're still very active in doing research in what we call project production systems management. Professor Hastak mentioned I was recognized by the Lean Construction Institute as a Lean pioneer, and you see me here with my colleague Glenn Ballard and wellichtig recognized for this award. So today I wanted to give you some really foundational knowledge, like what's new about this lean thinking. And I should add, I'm actually very agnostic about the term, whether you call it lean or not. I really could care less. It just gives us a way to talk about things. If you want to call it something else, that's fine. It's really about applying the scientific method in understanding our current world and trying to improve performance according to the objectives that we have. And so what I'll do in this presentation is I'm going to use this analogy of what we are very well familiar with in our built environment. It's building buildings, it's building houses, and I will segue from there into our new managerial thinking. I have a glass of water, thank you. Yes. Right, so houses, of course, buildings sit on a foundation. You need the foundation to be level, to be steady. If you can't start there, then obviously it's not very useful to build anything on top of it. The types of things that we build on top of the foundation are, on the one hand, the walls, the enclosures that protect us from the environment. And then on the other side, of course, we also have to build the openings in these walls to let light in, to let air in, and those kind of things. And then at the top, we have our objectives. We put a roof on top. We pursue aesthetic values, functionality, sustainability values, and so forth. So as far as engineering and design goes, we have very detailed, specialized engineering methods to, for example, engineer a foundation, to engineer the structure, to engineer the air conditioning systems, and so forth. But of course, what's really important about the functionality of this house is that all the different systems have to work together, right? They have to be attuned to one another. It isn't just about optimizing one part and ignoring the other parts, right? So in Lean, we very much talk about systems engineering and applying the scientific method for that. So here's the metaphor that Toyota uses to describe their Toyota production systems. So the reason for segueing into Toyota is that besides this aha moment that I and colleagues had about there's something missing in our managerial theories for project management, around the same time in the 1980s, early 1990s, it became very well known to the world as to how Toyota was designing and making cars. And it turns out that in the course of about 50 years, Toyota became from a virtually nothing company into the world's biggest, best car maker globally. And you can imagine, especially the American automobile industry was very much in shock about that being the case because they had been very much at the forefront of designing newer and better cars. And how could it be that there is this Japanese company that does things differently? So a large study was commissioned, performed by people at Harvard and MIT. They went to Japan, they studied the Japanese methods, and they realized it wasn't specifically Japanese method, but it was Toyota that had very much figured out a different way of designing things and building things. The person you see on the right-hand side is Taiichi Ono. He was one of the industrial engineers very much driving within Toyota new management methods and inventing many new management methods, also inspired by other management principles and a very relentless pursuit of quality. Right, around 2000, Toyota developed an internal document that described their managerial methods in a very systematic way and depicted it in this house of Toyota. And so very similarly to the way we design and build houses, of course, there is a strong foundation that you need, the Toyota way philosophy ultimately that governs everything else in their organization. We need to have a level base, we need to have a stability in our production system in order to be able to move ahead. On the left-hand side, you see what's called the just-in-time pillar of the Toyota production system. I'm sure many of you have heard about just-in-time before. We call just-in-time the go pillar of the Toyota production system, as in you want to move forward, you want to design things, you want to fabricate things, you want to deliver products, and you want to deliver services, right? So the thinking applies to a very broad set of applications. So on the left-hand side, the go pillar, and the counterpart on the right-hand side is, I think you guessed it, the stop pillar, right? The left-hand side is go. Of course, you want to go and meet your customer requirements and move as fast as you can, as you should. However, if something is wrong, you should stop, fix your problem, and then go back to go, right? So there is a constant going back and forth between the methods, and all the methods need, of course, to work together, like very tightly controlled gear system. You cannot choose this one part of the Toyota production system and think that you're going to be successful. Of course, you need to start somewhere, but if you really want to do it well, you need to do many, many different things at the same time. Right, at the top then we have the objectives. We want to deliver, deliver the best quality at the lowest cost, shortest lead time, best safety, high morale. And of course in the middle then we have people. People are very much part of the system. Production systems are socio-technical systems, so yes, technologies matter a lot, but ultimately we deliver value to people, and we will have people in the loop in many different locations, in many different managerial practices, and so we need to recognize that and take advantage of it, right? People are creative, and people want to have fun, and that's ultimately why we want to do what we do in our daily lives. All right. So that is the Toyota production system, kind of in a nutshell. Next, I will start to focus on this left-hand side, the just-in-time part. So it's the go part. In construction, of course, the go part is very much governed by what we call planning. So I should say a little bit more about planning. Right, so, what is the value of planning, right? And let me first put up some truisms. I hope you will agree. It is difficult to make predictions, especially about the future. Plans are forecasts. Forecasts are always wrong. The further out in the future you plan, the more wrong you are. The more detail you plan, the more wrong you are. Does that sound fair? So if we know we're going to be wrong, why bother? Kind of a fundamental question. So why do we plan? Well, we plan because we have a vision in mind. We plan because we want to accomplish something in the future. And by planning, we can lay the preconditions, we can define our actions, we can coordinate with other people to synchronize their actions so that it makes it more likely that we will achieve that future that we desire to have, right? And therefore, planning is absolutely core to like everything and anything you do, right? It's your ability to possibly influence the future. So it's really important. Right, so then how do we think about planning? What does planning look like? So in traditional project management, we think of it in this way. You have this very big scope of work that needs to be done. Of course, it's much too big to do everything at once, so we're going to break it down in smaller pieces. We can specialize. Different people will be better at doing certain smaller pieces of the whole. So doing the work here is called transformation. To do the work, you need certain inputs. You have certain methods to execute, and you would produce certain outputs. And then we break the whole down in smaller pieces. We give one piece to one team, one piece to another team, one piece to another team. And in this approach of divide and conquer, our assumptions are that if we can do every piece as optimally as possible, we think that we will also perform the project in the most optimal way, right? And that seems reasonable, and that is true, but only in one condition. And the one condition is that you can break down the whole in pieces that are totally independent of each other, right? Now, that in reality never happens, right? The pieces that you have, you can handle them as independent pieces, but they will have interdependencies between them. And you can sever the interdependencies in going from the whole and breaking it down in pieces. You can break the interdependencies so you can address the smaller chunks. But you will find when you put the smaller chunks together, right, that maybe they don't go as well together as you had imagined to start with, right? Maybe the whole, therefore, is not produced as optimally as you can. So the knowledge that we have, the model that we have in mind as planning, as dividing and conquering, maybe we should describe it as work as imagined, right? We divide the work and then we think, oh, this work is going to be done in this and this way, right? And as unfortunately many of us do, is like, we hope that everything goes as planned. But is that the case? What is the chance that everything will go as planned, right? Again, 0 chance, right? Things will not happen as planned. So the counterpart of work as imagined is what we call work as done. And I'll give you one example and see if that resonates with you. Somebody thought, no parking anytime. Somebody else thought, oh, why don't I park here? Does this happen in construction? It happens all the time. It happens everywhere else, right? Somebody plans something, this is imagine what's going to happen, and then there's other people, and they may or may not follow the instructions. They may or may not even know the instructions, right? Of course, in this case, it's pretty obvious, but there are many other reasons why people may not do what the planner had anticipated, right? People come in with different perspectives. Maybe the drawings, the specifications are not so clear. There's some ambiguity in it. There's many, many reasons. Sometimes people are creative. They have better ways of doing that, what you actually ask them to do. So many good reasons. I don't need to expand on that. But what I do want to expand on is this notion that as we plan, we describe what we think should happen, right? This is what we think should happen. Now, the reality is that what can happen is oftentimes quite different from what should happen. You may need ingredients. There are certain prerequisites that need to be satisfied for you to be able to do what you should be doing. And ultimately, what people do themselves, what they commit to doing, what they will do, is quite different from both what they should do and what they can do, right? So here's one way to depict that. And I try to plot them out here in a few combinations in relationship to one another. So the master schedule, the master plan is what we call what you should be doing. Oftentimes, many of the tasks on the should cannot be done, and some tasks can be done, and then the people that are actually going to do the work will make commitment, will say, I will do what can be done, what I should be doing, but they don't fully overlap with each other. They're subsets of each other. There are also many situations in the middle of this slide over here, and on the right-hand side of the slide over there, where the should and can have different relationships to each other. Should, will, and can have different relationships to each other. Oftentimes, people are told that they should be doing something, and they say, yes, sir, yes, ma'am, I will do it. And then they start working, and they find that they cannot do it, right? And so if these situations arise, you appreciate we have a problem. And that's really what our lean thinking is trying to identify, first of all, and then secondly, of course, to remedy. So how does the identification work? So it's through a scientific method. You introduce metrics. You begin to gauge how reliable your performance is of the system. And then based on that reliability measurement, hopefully you can learn something from it and you can improve your performance. So the reliability metric is what we call % plan complete. And this is something you can try at home. The idea is that at the start of the week, you make a plan for everything that you're going to do, start and finish in the course of the week. Or choose any other time period, but just let's think about a week. You will write down everything that you will start and finish in that week, right? Now imagine yourself coming back at the end of that week and checking off which of the things that I said I was going to do, start and finish this week, which of the things did I actually start and finish, right? Do you think there will be any that you did not start and finish? Probably some, right? We can calculate a ratio, right? We can count how many things were on our plan. We can count how many we actually did, right? What do you think does that ratio look like? It's not 100%. It's probably not 0% either. But is it 20%, 30%, 60%, 70%? Okay, you try this at home, right? Next week, try it out. But let's assume it's 50%. Let's assume it's 50%. Why does it matter? What do we learn from this metric? Well, 50% means you were going to do so many tasks, and you've actually done half of them. So you had planned to do so many tasks, and you accomplished half of them. So what does that mean for your next planning period? Well, you have to replan what you didn't do because you still have to do it, right? So now you created rework in your planning process. So that's not good. You may be able to do the work next week, or maybe sometime further out in the future, you may have to come back to it a few times in order to be able to perform your work, right? So that's not good. You want high PPC. So it's not good for you, but I'd like to say it's actually not good for anyone else in the system either, because if somebody was going to produce some work for me and hand it off to me on Friday, and on my week work plan for the following week, I was counting on having their input so that I can do my work. If they don't accomplish their work, guess what? I can't do my work either, right? So there is this ripple effect through your schedule if things don't get done as planned. And so that instability is really detrimental to performance. So we want to increase the PPC metric, right? We want to increase our plan reliability. That's a very important aspect. So in order to do that, I'm not going to expand on the whole system. I'm happy to answer questions or talk to you in greater detail later. But obviously what we need to do is we need to make this connection between all the things that we should be doing at this very high level that you specify at the business case definition or the master scheduling or phase scheduling when we bring in different specialists involved in our production system to talk to one another about what they can do and cannot do. So we move from the should level to the can level. We develop look-ahead plans where we actively remove constraints so that all the work that we should do can be done. And then at the lowest level, we're moving from can to individual production units making commitments that they will do what they can do and should do. And then if things still don't go as planned, unfortunately, despite the best efforts, if they didn't do what they said they would do and could do and should do, then we can analyze the causes of this inability and we can act on the causes. Is it a supply chain problem? Is it a lack of knowledge? Do they need more training? Is it poor instructions? You know, whatever the requirements are. So we can catch the mistake immediately and prevent that mistake from happening again. Right, so that system is what we call the last planner system. Now, the last planner system begins to address this transformation problem where we need to understand interdependencies and we need to understand the difference between work as imagined and work as done. But there's other parts that we need to consider in our production systems. So the transformation model is very much this input-output model. For those of you who've been doing scheduling, you know, when we develop our CPM schedules, we simply define precedence relationships between activities, finish to start, and so forth. But we don't really say anything more about what the preconditions are for starting work. And there's usually a lot more to be said besides resources. We need to figure out materials, for example, and instructions and so forth. So taking a step back, in addition to us understanding that there were some pieces missing in the language of project management, such as space, and in addition to understanding that breaking a whole in pieces, solving the pieces and putting it back together is not going to give us the optimal solution. We also looked at other bodies of literature out there. And besides the project management literature, which very much is transformation-based, in industrial engineering, there's also a whole body of literature that has to do with queuing theory, the theory of the waiting lines. And what's really useful in the theory of waiting lines is that besides activities, as you could see over here, like loading a piece of equipment or a truck, we also model these elements here, which are called queues. And queues are holding positions where resources will be waiting for useful engagement in some activity. So we can begin to articulate what the handoffs are between the different parties. And that proves to be really important because these handoffs determine whether you can do what you should be doing. So we can learn a lot from queuing theory, or in generally speaking from models that describe the flow of resources and how effective these flows are. And then you will see on my drawing here another dimension, the vertical axis. The vertical axis is what we call the value axis in this framework. And the value axis is orthogonal to the two other ones. The value axis basically says, well, it's all well and good that you can transform things, inputs into outputs, and do that very well. And it's also even better if you can do it without big queues in between the different activities. But what good is it if nobody wants your service or if nobody wants your output, right? What you do needs to be of value to somebody. Otherwise, there's no point. Yeah? And I have two rings displayed there to describe that what is of value is actually very different from how much something is going to cost, right? So you can see two rings there, a very fancy engagement ring with a big diamond on it in the marketplace, may cost $10,000, let's say. Above that is my engagement ring. There's a tiny little diamond on it. Yes, it's 18 karat gold, but altogether it's probably worth like $1,000 if you try to pawn it, right? But to me, right, it's priceless, right? To me, it's of so much more value than this other engagement ring. So value is something very personal, and back to production systems being socio-technical production systems, people really matter because in terms, we define value, right? We define what sustainability is, we define what aesthetic values we have, and so forth. And it's very separate from understanding transformation and flow. Right. So the theory that we have been pursuing here, as identified by my colleague Lauri Koskela, we call it a transformation flow value perspective on production. And the important thing is you need to do all three, of course, and you need to balance, right? You don't want to optimize one at the expense of the other, but you're not going to be perfect in all three at the same time, right? So you need to begin to weigh. You're going from one to the other. All right, back to the house of the Yoda. So with that, we've talked about kind of the big picture of planning, why planning is so important. Next, I'd like to expand a little bit on research that I've been working on, which has to do with takt time planning and creating continuous flow. So it really highlights this flow perspectives and uses that to augment what we do in the transformation view of planning. Right. My buttons here. So what is takt? What is takt planning? You could see it here with the metronome. Right? Takt is all about establishing a regular beat for production, and the beat is determined, of course, by value, by what the customer wants. If you're going to sell a car to customers and you have the demand for your product at 1 car per minute, then you need to produce at 1 car per minute, right? So we have a demand for the product that is going to help find the takt, and now we can use that takt to actually engineer our project production system. And where does takt planning fit in the last planner system? I think it fits at many different levels. I'll talk today a little bit about operational takt planning, which is how do you actually develop that schedule, that plan, that gets us from the should to the can. But of course, anytime you're going to change the way we manage and the way we produce things, you need to get everybody on board to understand what the requirements are. And if you want your subcontractors to do anything different from what they're used to, you better tell them before you sign the contract, right? So you need to understand the supply chain implications and make sure that you can align the supply chain to the requirements of the projects. All right, takt planning, what are the objectives in the system? Well, we have trades involved. There are trade specialists. We obviously want to tap into their expertise. They know how to do the work. Let's figure out, let's ask them how they want to do the work, and let's try to let them work in the way they prefer, because that's why you have specialists on board. We'd like to aim for constant crew size and continuous workflow. Constant crew size, it helps with improving productivity. It also helps with safety performance, and there are many other reasons why that is a good thing. We want at all costs to avoid trade stacking. So we don't want different trades to be on top of each other. And so the rule in takt planning is 1 trade in any location at any one time. Okay? And then, of course, we want to use timely takt handoffs. And then, ultimately, we want to push the whole production system to match the speed that is required by our customer. So a little bit more detail, since I think this is a new topic for many of you. So what we do in takt planning, I said this is the operational takt planning. So at this point, we know who the subcontractors are, so we can actually go look at the drawings and specifications so he understands their scope of work. We can pick a part of the site, maybe a floor, and we can map out with these specialists what steps they need to perform and who's going to come first and next and so forth. So we do this process diagram at the top here with sticky notes for color-coded for each different trades. Some trades may not care who comes first, but they know where they fit in the sequence, and so we'll have to resolve who is going to come first, who's going to come next, because we only want 1 trade at any space at any one time. For each of these scopes now, for the work area that we've carved out, we can go and measure how much time they will take given the means and methods that the crew will use and the crew size that they will bring to your site. These are the blue bars in our diagram over here. And so what we've done in this workload histogram is we've linearized all the production steps. You see in here that the electrical contractor comes before mechanical, and then later we resolve it a different way just to illustrate mechanical comes before electrical. The sequence doesn't really matter from a takt planning perspective. It matters, of course, in execution. Anyway, different trades will require different amounts of time, and the whole idea is that we want to give everybody the same amount of time. Therefore, if everybody's going to get the same amount of time for a given area, obviously you need to define what's called this operable tact. You need to use the maximum in your workload histogram and give that amount of time to everybody who's going to come through your space. Right now, whether your operable tact meets your customer demand, that's a different question. And there's different things we can do about that. If the operable tact, for example, is too large, if it takes too much time relative to the customer tact, maybe we need to assign more resources, for example, and then the bar will get lowered. I don't want to expand on that right now. But we want everybody to walk in a parade of trade. So then what does our schedule look like? Well, if we give the whole floor to one trade at a time, then of course they'll have a lot of work on that floor. It's going to take whatever that workload peak amount of time is for every trade to get through there, and we're going to have a very long schedule duration, right? So what can we do to make the duration shorter? We will, in fact, divide the workspace into smaller sections, and we will do it in such a way that we try to balance the workloads, right? So as you can see intentionally here, these different locations may have different boundaries, different shapes. What we want to do is look at all the trades we need to go through each of these locations, how much time they need, and again, we want to calculate that operable tact and see if it meets our customer tact. And so by dividing the workspace into smaller pieces, we can now allow trade 1 to start in location 1, and when finished, they will move to location 2. As you can see over here, location 1, location 2, and then they'll move on to location 3. There is nice continuous flow for the crew. And in location 1, of course, the whole parade of trades is going to come through in the sequence that we have specified. So this is what a tact plan looks like. It's very different from a normal schedule, right? So why would we prefer it over a normal schedule? The reason why we would prefer it, first of all, is because we've had extensive conversation with the trades involved to figure out what they need to do to build a facility, what resources are going to be required. We've had the trades talk to each other so they can understand the right sequencing, the sequencing that they prefer. So we already have significant clarity about the work. But on top of that, in execution, of course, it becomes really obvious as to who needs to be where and when. And if you leave materials after you finished your work, you know that you're going to block the other trade, and you know exactly who's going to get at you. So you don't need a superintendent to come yell at one subcontractor or another, like you left your materials there. You need to clean them out of the way. It becomes more conversation between the foremen, like, you know, this was our plan, you are in my way. Go figure it out. So it really decentralizes this coordination problem, and it makes it much more effective. Right, so that's how we create flow in our production systems. Every step gets the same amount of time. We're very clear on locations. And with that, of course, because we now have this kind of train of activities, we must have perfect execution, and we must have impeccable coordination, right? Perfect execution. So what does that mean? We need to have good process capability. Every trade needs to know when they're in an area that they can for sure be done with the work in that area within the tact. Usually they'll have a little extra time to finish, but they must get it done within the tact, because you know immediately what the consequences are for the rest of the schedule if they're late, right? So that's important. So we must relentlessly eliminate bad variability in execution. We must be reliable in the time that it takes. And we must make sure that there are no defects, no rework, no coming back to areas because you forgot to do something or because you didn't have the materials, right? That these are essential requirements. And this is really where this house of Toyota with all these different managerial methods comes in. It's like you can't do tact planning unless you really pay attention to all these other components at the same time. So with that, let me move on here. One of the things that you really need to do well is to make sure that when somebody performs work in a certain area, and they'll have to relocate to another area and relocate to another area as opposed to having the whole floor to themselves, you want to make sure that they can relocate without a huge penalty, right? That it's easy to move from one location to another location. And likewise, of course, you need to tune your supply system so that when you are in a location, you have exactly what you want, what you need, nothing missing, right? Impeccable execution. And you don't want to have too much excess, because any excess stuff you're going to have to move, and that's going to cost you extra work. So what does the quick changeover and what does integrated logistics look like? You may wonder. I'll give you an example here from a plumbing contractor working on a hospital project. So what have they done here? Well, first of all, you notice that they have a cart. Everything, as you can see here, is on wheels. So it's very easy to load these materials to the site. You will see that their cart here has these rectangles, right? So it's easy to lift this with a forklift and move it off the truck and onto whatever floor level you need to be. An important thing we learned is you want to make sure that these carts have brakes, just for reference. It's really important. But anyway, I think it's easy to move, right? So you can easily relocate from one location to another location. Easily move on site, easily move off site. The other thing that you see here is there's different components. These are quite extensively prefabricated, right? Many different parts have already been put together on it. You can see even the faucets are attached to it. Some of the drain pipe is attached to it. So this plumber has gone through extensive lengths to prefabricate, and by fabricating, of course, they lower the amount of time that they need on site to do their work. So that helps them stick to very short takt times. And then the other thing that's happened, of course, is kitting. So in some of these components, you can see that there's some additional parts provided that maybe they couldn't quite attach to the assembly that they have made. You want to make sure that everything comes together so that your crew doesn't have to wander off left and right to find what it is they need. Okay? So that's what lean logistics looks like. Now, I mentioned before, plans are forecasts are always wrong. Despite the best planning, things can go wrong. So in the Toyota production system, then if things go wrong, we have to jump to the other side here, the Jijoka side or the automation side. And in the automation side, I wanted to highlight two specific things. One is the automatic stops, and the other thing is error proofing. So as to automatic stops, going back in history here, this is a loom, a weaving machine. It's very important as a historic piece in the history of technology. This machine actually in 1924 was outfitted by Toyota family at the time. Toyota family, before they made cars, they actually were in the weaving business. They started in the weaving business in the late 1800s. And they were very ingenious in designing these looms and automating them, even to the point that they had patents, and they would license these patents to the British, right? The British, who of course had an extensive weaving industry well before the Japanese. Anyway, what's special about this loom is that, of course, with the loom, you have a shuttle going back and forth, and every once in a while, a thread breaks. And as soon as a thread breaks, of course, you're going to have a defect in your fabric. And the sad thing about that is, well, besides having the defect, depending on how much fabric you already have produced, maybe you have to throw everything away because there's nothing you can do with a piece of fabric that you already have. So it's costly to have defects, right? That's true for weaving, that's true for anything. It's always costly to have defects. So Sakichi Toyoda at the time defined an ingenious mechanical way for this weaving machine to automatically stop if one of the thread broke. So he had a counterweight mechanism, and as soon as the tension stopped, the whole machine stopped. So why is this good, right? You're still making a defect. The good thing about it is, before that, you had to have one person per machine keeping an eye on whether the machine was continuously working. Now, if the machine automatically stops, you can have one person supervising 10 machines, 20 machines. Right? And that's really the notion of the Jidoka, or the automation part. It's having people work with machines, but not having people kind of stand there and staring at the machine, you know, is something right, is something wrong. It's really about letting the machine do its own thing until it needs attention. Right? So stopping is very important. The other part that's really important, let me show you this one, has to do with making it really easy for people to do their work and to not make mistakes. And there are many different techniques to do that. I have here a very simple example. I think many of you will be familiar with little widgets like this with all these different types of connectors. Obviously, what you see here is a nice solution to coming up with connectors, making sure that you have the right connector at the right time in the right place. You just provide flexibility. You just tie them all together. You always bring all of them all the time, and then, you know, you'll have the right one when needed, Yeah. And these widgets come in different colors. So let me ask you this question. Who likes the black one as opposed to the red one? Who likes black? Some of you. Who likes red? I like red. Is there a difference, a material difference? It's a matter of aesthetics, right? Colors and taste, we don't have to argue about. Different people like different things. One will buy the black one will buy the red one. All right, on the right-hand side, you have 5 different connections. How many colors? 4 colors. Why do you think does the manufacturer make it that way? Obviously, they had black and red, and they added green and blue, RGB colors. That makes 4 colors. But they needed 5, and they used green twice, right? So this is kind of manufacturer convenience. Does it help you as a customer that these are different colors? Well, it helps you if they're different colors, right? So you can say, I always need the blue one for this situation, or I always need a red one for this situation. So in that sense, there's an advantage of having the color coding as opposed to having everything of the same color. Color coding is very useful. However, if you have 2 of green, it's like, what gives, right? Why couldn't you just choose another color as well? So this is what we're thinking about when we think about mistake proofing, when we think about what can go wrong, and how do we make it easier for people to not do things wrong, right? Not pick the wrong one. So this color coding didn't quite work out as far as I'm concerned here. But the connection pieces worked well. We built in flexibility, and you can build in flexibility with providing like all the different options, but that's a rather costly implementation. We think of flexibility also in other ways. You can see here the USB Type A connection. There's no symmetry here, although there's only one way to plug that into your computer, right? Now think about when you last tried this. How many tries did you have to plug it in, right? If you're lucky, it's 1. If you're not lucky, it's 2. Sometimes it's 3, yes? So if it's 3, you've just taken 3 times as long as it should have taken. Yes? Not good. Not good, right? Every detail matters. So the USB Type-C, of course, is better because there's no up and down. You just can plug it in. But of course, something that's symmetrical accommodates even more opportunities, right? The headphone jack is all around. There's only one way to plug it in. So obviously, that's a much better design. So if we can design things to be kind of more universal, then we can save people time doing things wrong. I put in here an example from an electrical light fixture manufacturer. Obviously, plug-in wire harnesses have major advantages. You can't cross-wire your electrical wires. You will plug it in only in one way, and you will know that it's done right. In fact, you and I can do it. We don't need great electrical training skills to make these connections. So we've greatly simplified the work. And again, this all feeds into doing tactile planning and ensuring that things are done correctly. So we need to make our systems kind of tolerant of multiple actions or enforcing the correct action. I mentioned color coding is very useful. I'll give you some more examples of color coding. On the left-hand side here, you see a blueprint of a hospital facility where there are many, many different types of wall. Obviously, if everything were in black and white, it would be rather difficult to know what is where. For quantity takeoff purposes, obviously for construction purposes, doing a little color coding makes very good sense. It just makes it much more clear as to what wall type you're going to need in which location. And color coding can be used on many, many different things. On the right-hand side, you see color-coded nails. Nails of different lengths have different colored heads. Certainly helps the carpenter who's doing the work, who will know I'm now using the blue nails in this location and the red nails in this location. And of course, what's nice about it also helps the inspectors know that the right nail is used in the right location, because nails get nailed into something, so you actually don't see how long they are once they're nailed into something. So by allowing the nail head to have a color, you can visually inspect whether the right component is in the right place. So color coding is very useful, but we don't want to do it randomly, right? Many of you haven't spent a lot of time figuring out what the conventions are, but there are some conventions in color coding. And for that, I can highly recommend that you read some of the books by Edward Tufte. Edward Tufte is an engineering professor, and he discovered that graphical communication in engineering is super duper important. And if you don't do it very well, you may not get your ideas across. So I would all urge you to really think twice when you pop that next graph from Microsoft Word or from Google in your document and kind of use the default settings. Don't think that the default settings, in fact, are good settings, right? Don't think that they're good. You really need to think about what you want to convey and how to get the colors right. Because what happens when you don't get the colors right, right? And what does right mean? So here we have a map, right? And on the left-hand side, you see a very nice depiction of what the color coding looks like. The taller mountain is darker, and we go to sea level, and the deeper the sea is, the darker it is, right? And I think you can look at this map. It's very intuitive. What if we change the colors? Oops, and now, right? And this is only half of the picture that changed colors, mind you, right? Only the sea level has changed colors. But you change colors and it becomes incomprehensible, right? So if you don't choose the colors according to whatever the shared understanding is within your community, then you create complexity, right? You make it much more difficult to understand what's going on. We call this self-inflicted complexity, right? This is self-inflicted complexity. So admittedly, our world is complex, right? And it becomes increasingly more complex, but we're not all the victims of fate, right? It's not just that things are the way they are. Some of the complexity that we see is complexity that we do to ourselves. And this is a good example of it. So some of the complexity you can design out when you design a very good project production system, whether it's through color coding and visual management, whether it's through tact planning, where you create very much regularity in execution. There are many, many other ways where you can simplify and just make it much easier for people to understand what is expected, what to do, and you make it much more likely that your plan is going to be executed as planned. So with that, let's get back to our house of Toyota. We've talked about just-in-time, we've talked about the Yudoka. You can understand that by reducing the self-inflicted complexity, we create more stability in the production system, which then means it's more controllable and more executable to ultimately achieve the best quality and best time performance and so forth that we want to have. So with that, this is the takeaway of this class. I think you want to understand the distinction between work is imagined versus work is done. They will always be different. And what can you do to reduce the difference, right? Lean is about understanding that there will be variation in the system. There will be good variation, there will be bad variation. Good variation is the variation that we want. We don't want to eat the same thing every day. We don't want all the buildings to look the same. There's a lot of good variation intentionally created. But by definition, all the variation that is not explicitly recognized as good variation is bad variation, and you need to get rid of that, right? Because that's where the waste is. The good variation is where you create value. The bad variation is where the waste is. And that's really what the lean thinking is about, right? It's understanding these two things, and they're separate, right? It's not because you're eliminating waste that you're necessarily creating value, and it's not because you're creating value that necessarily you do it with the least amount of waste, right? So they're different things. But in order to have good production system performance, you need to do all of those. And with that, I will leave you to ponder what I've presented and see if you have any questions.
Great, thank you very much. Let's give a big round. So I'm sure you're bursting with questions, so please go ahead. We have online also. We have, if you have any questions, those who are online, please open your mic and ask. Or if you raise your hand, we have somebody monitoring it today also, so we can do that. Yes, go ahead, please.
Thank you so much for that awesome presentation.
Turn on the mic, please. There we go.
So something that really caught my eye was when you started talking about the space as because typically we don't see that. We see it more like a constraint when we're doing the last planner. It's more like a constraint. And I was thinking, what will make us think that it should be a resource. Like, for instance, I was thinking also technology then should be a resource, because that's something that if it's not available or is available, if in different countries there are different technologies that I can use, I can get more of that. Like, for instance, in space, I can have warehouses, satellite warehouses, so it's something I can get. What will be the characteristics that make that these should be considered a resources and not constraint or other things?
Yeah, I mean, so the general categorization is we talk about time and money as resources, and then materials, manpower, and machines as resources. And so I put space there. I would put, information and technology maybe up there with either the machinery, the tools, or the materials, depending on how you classify it. So I think that's included there. I think space is very different in the sense that it's not a scalar variable, right? So time, you can add up time. It takes 5 minutes plus it takes 5 minutes. It's going to take 10 minutes. Same with money, same with number of people, same with number of machines, same with number of materials. Space is at least two-dimensional, if not three-dimensional. And so it really requires a different way of thinking about what it is. But you're right, you can have space here and you can have space there, and then you have twice the amount of space, perhaps. What's different with space, though, and really explicitly requires attention, is then you have a transportation distance also that you need to create, right? So again, space is a little bit different, and I think in that regard, much more difficult to manage. But it's a choice. Just like how much money you're going to spend or how many people you're going to have on a crew is a choice. So I would consider it to be a resource that you can manage.
Thank you.
Thank you. Thank you for the question. Yes, go ahead. Press your mic there. Thank you.
Thank you for the presentation. My question was when you talked about TAC planning, right? So when we link activities in TAC planning, do we have any wiggle room there, or do we provide any float, or are all the activities critical during that time?
Yeah, wonderful question, wonderful question. So let me go back to my picture here. It's probably easiest, then I don't have to use a whiteboard. So in this sense, as you see in the lower right here, in this sense, every activity is given the same amount of time, and on the schedule shows up with the same amount of time. And so from that perspective, everything is critical. No flow. No flow. However, what our traditional project management or CPM schedules don't talk about is variability in execution, right? So they assume that if you give 3 days for an activity that's going to take 3 days of an activity, does it take 3 days, like exactly 3 days to perform anything that you say is 3 days on the schedule? No. Probably not, right? I mean, hopefully they're done in 2.5 days or close to 3 days, but probably it doesn't take exactly 3 days. I mean, if things go badly, it may take 3.5 days, who knows? But there's variability in the system. So if you want to have reliability in that handoff from one step to another step, you have to do what's called underloading. Yeah? And underloading means you have to have some extra standby or swing capacity, whatever you call it. You have to have resource available to accommodate the variation in duration as it occurs in the moment, right? So you have to have, in a way, more people than you would assign, because you want to make sure, absolutely sure, that you're going to be done in time. And so what you see in this diagram, the operable tact, which you'd like to line up with the red line, right? The operable tact is defined by the workload peak in this histogram. You can see that all the other steps take less time, right? Now you can say, I don't want my resources to be wasting time standing around doing nothing. So this is then where production system design comes in, right? Maybe you had 4 people, let's say, for that first activity, and now you find out that 4 people is really too many because this activity is done in a much shorter time than your workload peak. Well, maybe you don't need 4 people, right? Maybe you need 3 people or 2 people, right? So because you have this histogram, you can begin to balance the workloads across the trades. This is not a conversation that we normally have, right? You can begin to balance. If the workload peak is much too large, you can begin to think about, how can I make an investment, maybe take some of the work from one step, move it to another step, right? Rebalance the workloads. Maybe take out some of the work, fabricate elsewhere. Maybe buy better tools and methods instead of painting with the paintbrush, right? Use a roller instead of using a roller, get a spray gun. you can begin to think in a rational way about what it takes to balance this production line. But so to your question, do activities have flowed? Well, actually, I mentioned in the strictest sense, nothing has flowed because everything on the schedule is given the same amount of time. In practice, everything has flowed because there will be variability in these workloads. And so, and intentionally in my drawing, my blue line doesn't touch the workload peak because there's underloading, right? And what I didn't show, to keep it simple, is I didn't show the variability on these workloads. But that's what you want to get, right? You want to get, to the extent you can, to 100% guarantee that you will be done within the TAC that you get in.
Yep, thank you. I had one more question.
Sure.
So you showed us an example of what lean logistics looks like.
Yes.
So in field, do subcontractors do that on their own, or do GCs or owners have to enforce that or ask them to do it? Or how does that look like in field?
If you were a subcontractor, what would you do?
I would say it depends on the money. Like if I'm getting if I'm getting paid enough, yeah, I'll do it. But
On which
Yeah.
money is the question?
sorry.
So it depends on which money. Is it the money in your project contract?
Yeah, like if I'm, let us say if I'm getting some kind of bonus for finishing my task faster, or let us say if I'm, yeah, if it specifically says in the contract I have to follow some maybe put in some lean logistics in there, I'll do it. But or if I had positive experience with lean logistics, then I will do it, right? Like, I don't know.
So certainly if your contract says that you should do it and you signed a contract, you should do it, right? There's no question there. But look at this example, right? The question is for you, do you think this is a one-time deal for this company? Does this company only do one project?
No, yeah, this
Probably
thing can
not,
be used.
right? You need
Yeah.
to make an investment in the carts. You need to make sure you have a forklift available. You need to make sure your fabrication shop is set up, with all the right padding and adjustable brackets and so forth. This is not a one-time deal. So if you're running your company, this is a specialty contractor. I can tell you they have been involved in lean projects. They do a lot of lean projects. But this type of investment, it's just a good business decision. Why would you not do it? Right? Let me give you an example, right? I don't know about you, but I really don't like to clean up my house. Right? I don't like, and the sad thing is it always takes too long. So should I invest in getting better at cleaning my house or not? What do you think? Yes?
What's the value proposition? Can you buy cleaning services that are of greater value to you than the time you spend cleaning?
Fair enough. So you can outsource it. Fair enough. But just from my own perspective, without outsourcing, should I try to get better or not?
Sure, yes.
Sure, because I really don't want to do this. So let me just get as good as I can at doing it and just get it over with, right? It has nothing to do with my project or anything else. This is my job. If I need to do it within my scope, I'm going to invest in doing it, and not just because I need to clean one room, but I need to clean my house, and I need to do this over and over and over again. So certainly, I want to get really good at it. Right? So you want to get really good not just at the things that you really like to do, but also at the things that you really don't like to do. But anyway, I think the important thing here is it's a long-term investment. Yeah,
Thank you.
Good questions. Yes, go ahead.
that's very good questions.
Press the mic button.
Okay, it's working. So my question is most related to the implementation part. So I know that in lean construction, communication is very important between different stakeholders. So how do you think we can efficiently communicate all those, for example, methods, all those information to all the stakeholders? Do you think using new technologies, such as, for example, building information modeling, can be helpful?
Sure. I mean, technologies, use them as you see fit, right? Why not? I mean, technologies, whether it's low tech or high tech, do it. Let me see if I can go back here. The question is, what's the problem with communication, right? What's the root cause of the communication? And technology can provide an answer. Your 6 and 9 example, you can say, maybe there's some way that I force people to look at the computer screen so there's only one interpretation. There's also a very low-tech answer, right? A very clean mistake-proofing answer is sometimes you put a little bar under the number, and you can see whether it's a 9 or a 6, and you resolve the ambiguity. So yes, technology can help, but I would suggest start with no technology, right? The very simple solution, and that way, if you can make your solution robust, like drawing a little bar under it, under the number, then your problem solved. Why bother with technology, right? So you don't want to implement technology for technology's sake, right? And the right-hand example, I'm afraid BIM is not going to help you.
Yeah.
Right? Technology is not going to be the answer.
Yeah,
It's a more fundamental problem. So yes, technology can help, as in the color coding, you know, of the different wall types. Obviously, you're not going to sit there with a marker and do that, right? You write a little code in Revit, and you just say this wall type, this color, and you're done. Certainly.
Yes.
But you need to think what's fit for purpose for the problems that you have.
Thank you. Thank you so much.
Thank you, Shiva. And let's go to Dulcie first. Dulcie, you had a question, then I'll come back.
So I just wanted to, okay, just two observations related to what Professor Tommelein said before. One has to do with the example that you gave with respect to cleaning your home and, you know, needing to be good in it. It also reduces the rework you have to do. Right? And that's an important part of adding value and reducing waste. So that's one observation. And the other observation or the other thought has to do with the use of technology. And I would like to use the word use of appropriate technology, right? So something which is, in this case, just the bar or a color code under the numbers versus, you know, something which may take a lot more effort and more resources. So I would say those would be two observations. Yes, technology is very, very good, but trying to figure out what is the appropriate technology is.
Yeah, it's not a solution in and by itself. Right?
Yes,
it's not
exactly.
like technology is going to solve all your problems, all
Yes.
your self-inflicted problems.
Yeah.
Right? You need to think about what they are.
And sometimes using technologies unwisely can lead to unintended consequences, right? So.
Thank you, Dulcie. Go ahead.
Hi, thank you so much for the presentation. That was amazing. I was just going back to the basics, you know, project versus process, open system, closed system, you know, minimize reward. How do you respond that, you know, these techniques with being construction is not applicable to projects where you have creativity, you know, it's not repetitive. Sometimes you have things that we cannot control. So, you know, I see that you're moving from a project to a process where the, something like the manufacturing that the product is moving, versus the project is, you know, constant, whereas the labor is moving. So, you know, some people would say that this is not applicable to each project. So, how do you respond to that?
Well, I mean, the International Group for Lean Construction has been around since 1993, and there's you know, we had our 32nd conference this year, so there's a lot of literature available that describes what can be done and what is done around the world on projects. So as far as that goes, I think plenty of evidence has been provided that it can apply to projects. Now, that being said, just like you have to choose technology appropriate for the problem at hand, you cannot just take everything Toyota does and replicate it and think that it's going to work. So, for example, the last planner system that I described, in fact, was developed before, you know, Glenn, in this case, knew about the Toyota production system. It really emerged from his own field experience as a foreman and productivity improvement consultant. So you don't want to necessarily copy, but you want to understand the principles and the methods, as in this House of Toyota. This House of Toyota doesn't talk at all about cars, right? Nothing to do with cars. So you want to understand the principles and methods and then say, within my context, how do they apply? And the other thing you have to recognize is what applies today doesn't necessarily apply tomorrow. So there's a story where some visitors go to Japan, they observe the Toyota production system, they see that Toyota is using a Kanban system, a card system to relay information from one station to another station. And this person says, aha, Kanban, let me go home and try Kanban system. And then they come back the next year and they go to their say and they say, oh, look, I've implemented this wonderful Kanban system, but now I look at your factory floor and you're no longer using Kanban. And they said, no, it's not necessary anymore. We now have a continuous flow process. It's not needed anymore. So what's needed today isn't necessarily needed tomorrow, right? Things change. And as you tinker with your system, as you improve it through continuous improvement, you may find that different methods are going to apply at different times. So you cannot just copy what's happening. You really need to think through, what am I trying to do here? So you're trying to identify variability. You try to identify good variability from bad variability, and you try to eliminate variability. That's bad variability. And then go figure out whether it's in healthcare or the postal service or anywhere. I mean, everybody is implementing lean principles.
Yeah, but some people will tell you that there's one project, one of a type. We don't want every old buildings to be.
No, and the cart that I showed you from the plumber, it's flexible, right? Because projects are different, and even within a project, there's significant variation, desired variation. So you do need to accommodate. For sure. Yeah, desired variation is good, right? This is also why we have people in the system, because they're creative, they come up with new solutions, and we want to be able to build, right, what the new solutions are. So good variability is exactly that, it's good variability.
Great, thank you for that question. I think we have 3 questions online,
Yeah.
so let's move to online.
Romano actually asked you, do you believe that IPD is a lean delivery model for construction? Many of the lean tools are used in IPD. We are experiencing IPD as the best delivery model for construction, which delivers best cost, schedule, and quality. So why do owners continue using conventional design bid build, which is more costly, takes longer, and reduces quality?
So first of all, a qualification on IPD. What is IPD?
Integrated project delivery approach.
Well, yes, thank you. Owen Matthews in the late 1990s was a mechanical contractor in Florida, and he's actually the gentleman who came up with the term integrated project delivery. And at the time, it was really about building a team of subcontractors who together would go after work. Now, that seemed like a good idea. Our lean community obviously understood and worked with Owen Matthews, learned from him what we could. Sutter Health, a large healthcare provider in Northern California, in the late 1990s, early 2000s, was looking for a new type of contracts. And at the time, there was no IPD contract per se, even though the name had been coined by Owen Matthews. And Sutter Health legal counsel, Wellichtig, you actually saw in this picture earlier on, went and developed a new contract from scratch, which is called the integrated form of agreement, which is not a transactional contract, like a one-on-one type contract between, let's say, the designer and the owner, the owner and the contractor would be one-on-one contracts, or in design build setting, a contract between the owner and the designer and the builder together. But it's a multi-party relational contract where you could have 10, 12, 15 companies all signed on the same agreement. I mentioned the integrated form of agreement because that was really created to be a lean contract. Now, history be what it is, the American Institute of Architects then came up with a contract called Integrated Project Delivery Contract, which has many notions and many concepts from the integrated form of agreement, but it isn't quite there. And nowadays, people have begun to add nuances, and on some projects you will hear, well, this is an IPD project. Some people will say, well, this is an IPD-ish project. And some people will say, well, this is a lean IPD project. So there you go. So, IPD itself, integrated project delivery itself, certainly doesn't say very much about what's going on, to put it shortly. I suggest that people who really want to implement lean practices, that you really look at this integrated form of agreement, which has merged into or has transformed into new types of contract documents, which are called consensus docs, and which are built much more around collaborative participation on a project. So it's a long answer to the question. But
No,
so,
thank you
yeah,
for that question.
you know.
And also from Majid, over the years, our local Toyota dealership has been known for importing used cars, primarily manufactured in Japan. However, recently there has been a shift in the inventory, which with imported cars now originating from Taiwan. I've observed discernible changes in the quality of this vehicle. Could you shed some light on what might be influencing this shift in quality?
Well, I don't know much about cars made in Taiwan, but Toyota, when they started making cars just before World War II, and then of course full speed after World War II, the first Japanese cars were terrible in terms of quality, absolutely terrible, and they got a bad name. And the cars were exported, but in the United States, nobody wanted to buy Japanese cars because they were really, really bad. But Toyota, gradually improved their practices, and they were very attuned to customer demand. And of course, the country that they came from, it's a very, very tight-knit social community, a country very tight on resources. They realized that one of the values that they wanted to have is fuel-efficient cars. And what changed the picture in the United States here is that when the oil embargoes, 2 oil embargoes in the 1970s happened, a lot of Americans began to look at cars that were more fuel efficient. And at that time, Japanese cars were getting better, and so obviously people switched to Toyotas and other made cars. So, quality, I mean, it's not a fixed thing, right? Quality is something you have to actively manage as you come out with new car models and new technologies, hybrids and plug-in hybrids, and the world doesn't stand still. As you do new product development, you need to, of course, design your production system around that with quality and other values in mind. Yeah.
Also from Catherine, how much does industrial psychology influence tax planning, especially the manpower resource? How much does industrial psychology influence tax planning, especially the manpower resource?
I'm not sure where she's going with the question, but I can add a few things, and it has to do with quality implementation as well. In traditional practices, if I can call them that, maybe not totally fair, but in traditional practices, when I'm, a trade of one kind and I see quality problems with the work of another trade, right? My usual response is, it's not my business. In Lean, we try to change the culture so that, if I see a problem that maybe belongs to somebody else's scope and for some reason they skipped, I'm encouraged to speak up because we have shared risks and rewards. Now, with that in mind, you need to have the right culture in place to be able to speak up, right? We don't always step forward even if we know that something is wrong. Sometimes you see something wrong and say, well, I can't really interrupt, right? Or it's really a small thing compared to what else is going on, and I'm just not going to bother. So we're working with this notion. It's called psychological safety. Amy Edmondson came up with this term in the 1990s, and she studied nurses in a hospital facility in urgent care, in emergency rooms. And obviously, if anybody sees anything wrong, whoever it is, whether it's a nurse or a doctor or anybody, you need to speak up in a moment, right? Because otherwise you can kill the person that you're trying to heal. So this notion of psychological safety also very much speaks into the quality management that we have. You need to have people who are enabled to talk about, mistake proofing is a good example. Everybody makes mistakes, right? To err is human. It's not like it's intentional. Many mistakes are made unintentionally, but you need to have a language to talk about it. And you need to have, of course, a way of describing what is a mistake and what is not a mistake. So again, there's a number of lean practices that fit into this psychological framework to make sure that we have the best quality that we can have.
Thank you for all those questions online. Let me move back to the audience here to see if there are any other questions. Well, yes, go ahead, Abby.
Thank you for your presentation. I like your example about self-inflicted complexity, and I was wondering if you could provide more examples about self-inflicted complexity.
Yeah, I mean, there's so many of them. And it borders a little bit on the question of, is it complexity or is it just complication, right? And we make distinction between complexity and complication. But let me give an example of self-inflicted complication. So when we send emails, email to me is a terrible tool because it's very linear in execution. Everybody reads their email at different times, and you can put many people in copy on the email, and some people send an email to somebody else one-on-one, and then the other person sends it with copy to 10 people, right? So now you have increased the communication from 1 to 10 if you copy 10 people. And then what happens if you make a mistake in your message, like you say, oh, I'll come to this meeting on Friday at noon, and you say, oh, and then the time changes, or you make a mistake, and you say, you know, on Friday at 11, right? Then you're going to have to send a whole new message at a different time to all these different people, which may or may not get the message because the message was forwarded in many different ways. So that's what I mean as an example of kind of self-inflicted complication. So if it would be much better if you had like a bulletin board, right, a shared display, and you just refer people to the shared display where you can keep the true north, you can keep what is current at that time in one place without exacerbating all this asynchronous communication with or without the right information. Yeah. So email we can do so much better than communicating by email. But anyway, I mean, other examples of complexity. It's like if you go to a hardware store and you look at how many different types of nuts and bolts there are, and even nuts and bolts of the same size, the same color, just with a different thread, right, or a different head. I mean, you have to wonder why do we need all these different nuts and bolts, right? Can we standardize? So I know of a steel fabricator in the Bay Area where they do structural steel fabrication, including welding. They were different weld fill materials that they could use, and there's different technologies that you can use in welding as well. The challenge is once you have more than one, once you have two choices, you create the opportunity to choose the wrong one. Yes? So simple, right? Simple logic. So obviously you're much better one to have only one. And so what they did is they invested in the most expensive option, that they have one option. It makes it so much simpler on the shop floor, right? All the welders are trained in that option. It makes their supply chain so much simpler, right? So what seems like a small thing actually has huge implications on the complexity of the system. You know, the more recent legislation in the European community to tell Apple that they need to be on the same page on the standard interface for chargers, right? That is huge, right? How many of these crazy connectors do we all have in our drawers because we didn't have the right connector at the time? You know, how much waste have we created, right? That's not very sustainable. So if we can agree on standards, it's amazing. I mean, just to give you another example, just recently I was working on a friend's house, and we were replacing the toilet seat, and I look at product variety, and so I thought my first reaction, I don't have any experience with them, but my first reaction was, oh gosh, what dimensions do I need to take here to know when I go to the store whether this seat is going to fit or not, right? Because you have to fit the bowl, but then you have two screws in the back, and what's the spacing, and right, could be complicated. So as an engineer, I took some pictures, and with my pictures I go to the store. It turns out in the United States, there's a standard. It's a standard dimension, standard, like all the toilet seats. There's the fasteners, that's it. It's beautiful. It's like, who cares about the fasteners, right? We care about the seat. There's only two shapes, round and oval. That's it. Beautiful. The rest is all aesthetics. So we've simplified it, right? This is great. This gets me excited. I'm sorry. This is lean, right? That's what self-inflicted complexity is. Right? You know things are going to work together. You don't have to break your head on it.
Yes, go ahead.
So now that you mentioned that self-inflicted complication,
Yes.
I worked for a long time in Peru, my country. We have the metric system there. And when I started working here, I remember I have a lot of problems with the carpenters because they have the measure tape.
Yes.
And they have fractions. And I was surprised how they were building and all the time have the same problems of how much is this, because the surveyors, the layout came and just put in the numbers in decimals. because they're using this engineering tape, and carpenters have the carpenter tape, and they're using fractions. And they receive call, because I was the surveying manager there, I will receive call every day, at least 4 calls or 5 calls, just regarding how do I read fractions and decimals. And it's something that sounds self-inflicted, but it's something you can manage. The system is like that. It's too late to try to change something like in the entire industry. So,
Well, there were efforts in the 1970s in the United States, I think it was under Carter, but correct me if I'm wrong,
To go metric.
Or Ford, even before, to try to implement a metric system in the United States, and very sadly it didn't work. The world would be so much simpler, and of course, I mean, the French had a revolution, right? At which time then they established the metric system. So there's some good rationale behind the metric system, like, you know, a decimal system, right, with multiples of tens. I got my engineering education in metric, and I still have a hard time with all the English units. So I'm obviously very biased towards the metric system. But if we could only agree on a standard, I think that would already be a big step forward. But unfortunately, we're a ways away from that.
Great question. We are running out of time, but if there's a pressing question, we can squeeze it in.
I should add, in terms of standard, I think in the world of computing, right, there is a global standard, and it is all metric. Right, all the computer connections and so on, they're all metric. They had the chance to do it right.
Well, so in the interest of time, I have a sheet full of questions. I'm not going to ask those.
Okay.
And so I had a follow-up question on complexity, but I think you have answered much of that, so I'll switch to a different question.
Please.
And that is that, you were talking about small batch production. So small batch has certain advantages, you can customize and you can have a smaller production, small inventory and so on and so forth, as opposed to a long production which has its own benefits. How would you say, so in construction, much of our activities could be stated as small production, small batch production. So what would be your thoughts in implementing lean principles so that we can get the advantages of long production?
Of
Long production.
long production, like big batches?
Batch production, yes.
Honestly, I think the advantages of big batches are overrated. I think they become self-fulfilling prophecies. So if you have a big truck, you're going to want to fill the big truck with many materials and maybe deliver more than you need. The reason why you want to do that is because you bought a big truck. Maybe you should have bought smaller trucks, right? So there's a lot of kind of self-inflicted practices. But one reason, Professor Hashtag, that you haven't mentioned as to why you want small batches, it's because you have frequent handoffs and you have immediate quality feedback. So if one thing is wrong, you would know that it's wrong, and you can take action to prevent the same from occurring over and over again. If you order 2 months worth of materials and they get fabricated, and then you find out that there was a dimensional error or whatever it is, everything is wrong. Right? So that is a really important part of it. But one-piece flow is the ideal. It cannot always be done. It may not always make economic sense because, as I said, we have investment in resources such as carts and trucks of certain sizes that kind of make it more tempting to use one batch size or another. But generally speaking, smaller batch sizes are better.
Thank you very much. I was thinking more in terms of, different projects being different. So when we move from one project to another, we're not necessarily carrying that productivity or production gain into the next project. So I was wondering, how we can manage that. So that leads to the question on complexity as well. That is it self-inflicted in our construction process, or is there a better way to think about perhaps modular construction to see that there is continuity from one project to another that need not get lost, and we need not say every project is unique. So your thoughts on that?
Well, I mean, exactly. I think modular construction is great. It takes this multi-project view, right? You can standardize your product families to accommodate certain circumstances, and then within your product family, you use what you have, right? Rather than recreating custom pieces over and over again. So I mean, it gets back to my toilet seat example. I think it's a good example. It's very modular. the things that nobody cares about really in terms of ultimate value is standardized, it's modularized out, and then you can focus on the aesthetics part. And I think at a grand scale, right, you first look at much bigger examples. I think if we can agree in the industry on certain dimensions, like we have 2x4s and 4x4s and whatever, I think, that goes a long way, right? It just, what you have. Okay, I'm going to go to the store. I don't need to get dimensions, exactly so. I just say, well, these are the parts that they will have. Let me just get what they have, and I can work with that. And then if you're smart, you can design your structure, so you don't have to do any sawing, you don't have to do any dimensional adjustments, because you can work with the standard components. So again, we need to do a lot more of modularization, standardization in the industry.
Yes, indeed. Thank you so much. This has been a very exciting presentation. Tons of questions. I'm sure if we stay here, there'll be a lot more questions coming up. So please give her a big round of applause.
Great questions.
Thank you all those who joined us online. As you all know, we'll come back again next week. So again, thank you very much. With that, we're signing off from Purdue University. Thank you.
Iris, excellent.